Hello, hi everyone, welcome back to the channel. So in this video lecture we'll be solving this problem, shortest path visiting all nodes. It's a Leetcode hard problem. So before you watch this video, before you need to understand the basics of graphs and its traversal algorithms like breadth first search and depth first search, and then you will be able to understand this problem well. So let's read the problem statement. We are given an undirected connected graph which has n nodes labeled from 0 to n minus 1. We are also given an array graph where each element in this graph array represents a list of nodes that are connected with node number I by an edge. What do we have to do in this problem? We have to return the length of the shortest path that visits every node of the graph. We may start from any node and stop at any node. We just have to visit all the nodes of the graph, and given that we may revisit nodes multiple times and we may reuse edges as well. Fine, so let's better understand the problem statement using an example. So let's take this example. We have 4 nodes. They are labeled from 0 to 3, and we want to find the shortest path, the length of the shortest path for this graph. So let's see the possible paths that we can have. So let's say the path starts from 1, then we move to node number 0, then we move to node number 2, then we move back to node number 0, then finally we move to node number 3. So this path from 1 to 0, 0 to 2, 2 to 0, 0 to 3 visits all the nodes of the graph, and it has a length of 4. So let's start from node number 2 now. We move from 2 to 0, move from 0 to 1, then from 1 to 0 back, then from 0 to 3, visiting all nodes of the graph. Okay, then we start from node number 3, move to node number 0, then move to node number 2, move back to node number 0, finally move to node number 1. Okay, so let's take another path. Start from node number 0, move to node number 1, move back to node number 0, then move to node number 2, move to node number 0, then move to node number 3. So the length of this path would be 5, while the length of these paths is 4. So these are the possible paths that we can have in this graph. So these are those paths which visits all the nodes of the graph, and the length of the shortest path would be 4. How many possible paths we can have in this graph? So in the worst case, we may have total 2 raised to the power n graph for n nodes. Okay, so what would be the answer for this test case? The answer would be 4, because these are the paths which are valid, which are the shortest paths, and they visit all the nodes of the given graph. Hence the answer for this test case is 4. How can we solve this problem? Let's see that. Okay, so there are few observations to understand the problem better. The first one is that this is a shortest path problem. The second one is that the graph is unweighted. The third thing to notice in the problem statement is that the n goes from 1 to 12. That means the largest graph that we can have has 12 nodes. Fine. So what does this suggest us? Since this is an unweighted graph, we want the shortest path. We can use a BFS. Obviously, BFS is the first option to find the shortest path in unweighted graphs. Now, what does this suggest us? N. Since we do not have any starting and ending vertex, we don't know where to start and where to end. We just know that we want to visit all the nodes of the graph, and the path through which we visit them must be shortest. And one of the option to think is explore all the possible paths. That means start from every node and explore all the paths. So how many paths there can be for n nodes? For n nodes, we know that there are 2 raised to the power n possible paths in the worst case. That means if n is 12, then 2 raised to the power 12 gives me roughly 4000 number. So we have 4000 paths which we have to visit, which we have to explore. That means we can just brute force this problem using BFS. It will pass the constraints of the problem. How do we do that? We know that what do we do in usual BFS? In a single source BFS, we start from the source node, we push that node into the queue, then we run a while loop and we pop the only node which we have in the loop and we explore its adjacent nodes. So in usual BFS, let's say we have 0 as the source node, we explore this node, then we explore its adjacent nodes, and in this fashion I will calculate the shortest distance till each node, and the weight of each edge is assumed to be 1. So let's say I want to find the, let's say we have this type of graph, we have node number 4, I want to find the shortest path till node number 4, and if I perform the BFS starting from node number 0, whenever we reach any node the very first time, then that means the length corresponding to the path through which we reach that node first time would be the minimum length. That's the idea in BFS. Fine. So keep that in mind and we'll generalize that idea to solve this problem. So what is different in this problem? We are not given any source vertex and destination vertex. That means we have to modify our BFS a little bit. How? But we can solve this problem using BFS. That means to do that, we start our BFS from each node. We make all the nodes as source nodes. So we push all the nodes into the queue and start running the BFS. Fine. I hope you're getting where we are going. Let's say we push node number 0, node number 1, node number 2, node number 3 into the queue. So what are the things that we have to keep track? Let's say we start from node number 0 and we want to explore all the paths starting from node number 0, and we want to select that path which visits all the nodes. So while starting from node number 0, we perform our BFS, and while performing the BFS, whenever we find a node where we have visited all the nodes of the graph, then the length corresponding to that node would be the answer. How? Let's see that. Initially we push all the nodes into the queue, and let's say we first explore node number 0, and corresponding to node number 0 we have to keep a visited array. So we keep a visited array corresponding to each node of the graph. Why? That means every node of the graph has its visited array. So we have visited array for node number 0, we have visited array for node number 1, we have visited array for node number 2 and 3. Similarly we have for node number 2 as well as for node number 3. So let's say this is for node number 2. This is because we are kind of using a multi-source BFS. We are assuming all the nodes to be source, and along with the nodes we have to push this visited array into the queue. So let's say we start from node number 0, we explore this node in the very first iteration. So that means node number 0 is marked visited, and then we explore its adjacent nodes. Let's explore node number 1. The path that we have till now has only node number 0. Now we explore node number 1. That means node number 1 is also visited, and the length here was 0, which becomes 1 here. Then that means 1 is added to the path. So we have explored this path 0, 1. Now I explore adjacent nodes of node number 1, which is 0 again. That means I pass this array. So here notice that I pass this array, the visited array, and this length to node number 0. So whenever I move from one node to another, I have to pass my visited array and my length to that node. First I moved from node number 0 to node number 1. I passed this pair to node number 1. Now I am moving back to node number 0. I will pass this pair to node number 0. That means the visited array that I am passing would be 1, 1, and this variable is 1. Here it was 1. Since I am adding one more edge, because I am traversing 0 again, then we are adding one more edge to the path, so this 1 will become 2. So we will have 2 here. Fine. So this is the path that we have visited till now. We started from 0, we moved to 1, then we moved back to 0. Then from node number 0 I will traverse node number 2 here, while passing this visited array and this length to its child. So here the visited array for node number 2 will become node number 0 visited, 1 visited, 2 will be visited, while the length till now will be 3. It was 2 here, one more node is added, it becomes 3. So here we add one more node or one more edge, which is node number 2. Then I move back to node number 0, and again I pass this pair to that node 0, and here the visited array that will have again would contain node number 2 visited, and this variable will become 4 here. So it will become 4 here. Now that means 0 is again added. We add one more edge. So we started from 0, we moved to 1, we moved back to 0, we moved to 2, now we move back to 0. Now we move from 0 to node number 3. Okay, so now while passing this pair to node number 3, that means the visited array that node number 3 will see would have 0, 1, 2 as visited, and while we traverse node number 3, we'll have node number 3 visited as well, while the length will become 5. That means I'm adding one more edge to node number 3, and here I check that all the nodes of this graph has been visited. That means we have at least one path through which we have visited all the nodes, and this is the length of that path. Fine. So while that means if we start from node number 0 and start visiting the nodes, then the path that we obtain will have length of 5, which visits all the nodes of the given graph. Now that same procedure must be repeated for all the nodes of the graph. So initially we push these 3 pairs, that is this visited array, this length variable, and the node itself. These three things are pushed into the queue for all the nodes of the graph, because we want to start BFS from all the nodes. So how would we make sure that we always obtain the shortest path? For that, I just have to start the multi-source BFS. So I push all the nodes. So I push this tuple for all the nodes in the graph, and I start my BFS search. So during the BFS search, whenever we arrive at a particular node, the first time when we find our visited array to be marked visited, that means all the nodes are marked visited, then the length corresponding to that tuple would be the minimum length. The same idea as we do in BFS. Whenever we arrive at a particular node, that path would be the shortest path. Fine. So here I just have to keep track when do I reach a particular node when I have all the nodes as visited. So now when I reach that state first time, then the node corresponding to that tuple is the last node in the graph, is the last node in the path, and the length corresponding to that tuple is the minimum length. That's the idea. Now here we have to make a little optimization, that since we are pushing a entire array for each node and passing this entire array to each node, that is, and we are consuming too much space, so we have to reduce this. How can we do that? So here is the trick. Let's say we have 4 nodes in the graph. They are numbered from 0 to 3. So what we can do is we can use bit masking. So what are bits? Bits, that means any number can be represented in the form of bits or binary form. So since we have 4 nodes, we take 4 binary bits, and this is the position number 0, this is the position number 1, this is the position number 2, and this is the position number 4. So this is the bit mask which we can use to represent a particular path. How? Let's say we want to represent a path in which node number 0 and node number 1 are present. Let's say we want to represent this path here, 0, 1. That means node number 0 and 1 are visited, so the bit mask corresponding to that path would be 0, 0, 1, 1. That means the nodes which are visited that means the bits corresponding to the nodes which are visited will be set, and the bits corresponding to the nodes which are not visited will be unset. Let's say I want to represent a path like this. So this path visits all the nodes of the given graph. That means the bit mask would be 1 1 1 1. This would be the bit mask. So let's say we have a path which visits 0 1 2. In that case, the bit mask would be this. So in this fashion, instead of passing an entire visited array, I pass this binary number or bit mask. How? So this can be represented in decimal form as 3, because this is at first position, that means 2 raised to the power 1, and this set bit is at 0th position, so 2 raised to the power 0, which is going to give me 3. So instead of passing this visited array, I just pass an integer number. Fine, that's the idea. That's called bit masking. So let's implement the ideas which we have explored here into a working solution. Okay, so this is the implementation. Before you move to my implementation, just try to implement the solution yourself from the knowledge which you have gained till now before you watch my implementation. So to represent that the tuple, I used a structure. So in this structure I have 3 variables: node, mask and cost. So this represents the node, this represents the bit mask, and this represents the cost for the particular node, cost for the particular path. Okay, so this mask is representing a particular path, while this node represents the last node of the path which we have. And here is the shortest path function which takes in the graph, and here we calculate the length of the graph, and we declare a queue of this type tuple, because we want to push these tuples into the queue. So this is the set. Why do we use the set here? So let's see why we are using set here. So while we were traversing the adjacent nodes of node number 0, so first we traverse node number 0, then we traverse node number 1, then in the next iteration I traversed node number 2. So I moved from 0, then I traversed 1, then I traversed 0 back. Now instead of traversing 1, I want to traverse node number 2. I have already traversed node number 1. That means at this point I have bit mask like this, and the ending node is 0. Now I don't push node number 1 again, that means I don't add node number 1 here or traverse this node again. I will store this bit mask along with the child node, that is 1, and these two things are unique. Fine, this pair is unique for every path. This will make sure that I do not revisit 1 again. I will visit next node 2. How? Because here I can see that, okay, so I'm claiming that this pair would be unique. So let's start from node number 0. That pair would be, the pair at this position would be 0 0 0 1, and 0 will be the node here. Then I move to adjacent node number 1. The pair would be 0 0 1 1 and 1. Now I traverse 0 again. The pair would be 0 0 1 1 and 0 as the ending node. That means I am representing 0 1 0 path. Now if I traverse node number 1 again, if I try to push node number 1 again, and the pair for node number 1 will be 0 0 1 1 1, because we have visited node 0 and 1, and 1 is the last node, while we already have this node pre-computed. So if somehow we store this node into the set, then we don't, and we check that, and when we check that this pair is already present in the set, that means this node has already been explored. We don't have to traverse this node back. So from 0 I traverse node number 2 again. So storing this pair helps storing this pair into the set helps us to revisiting the paths again and again. Fine. Otherwise, if we do not store this, then we start from node number 0, we go to node number 1, then we go to node number 0, then we move back to node number 1, and this cycle continues. To break this cycle, I store this pair into a set so that I can check at every node. So while traversing the adjacent node, I check if the corresponding pair for that node is already present or not. If it is present, then we don't have to traverse the node. If it is not present, then we have to traverse the node. That's why I'm using this set. Now here, I traverse all the nodes, and here I prepare my bit mask. So for node number 0, the mask would be 0, 0, 0, 1. Why? Because for a graph of nodes 4, only node number 0 is visited, then this would be the corresponding mask, and here I am setting that ith bit. So if I is 0, I am setting the 0th bit, and this is the corresponding mask for the path which has only 0. Then here I prepare that tuple. So the tuple for node number 0 would be node number, this mask which is this 0, 0, 0, 1. This basically represents 1, and cost. So the cost when we are starting is 1, and we push the node and we push this tuple into the queue while inserting, that is node and mask. So we have a mask here, not head, we have temp here. This is a little mistake, we have temp here. Okay, so and for let's say node number 1, the tuple would be 1, 0, 0, 1, 0 and 1. This would be the tuple for node number 2, for node number 1. So in this fashion I push all the tuples for all the nodes, and then I start my BFS. So here I start my BFS. This is the while loop, and I pop the front node from the queue, and I check if the mask for that corresponding node, if it contains all the bits set. So if for a mask of let's say 4 bits, the bits will be set when 2 raised to the power of 4 minus 1. This basically represents 1, 1, 1, 1. Fine. So if all the bits are set, then in that case this would be the cost. Why I am subtracting 1? Because initially I pushed a 1. The current cost minus 1 would be my answer. Otherwise, if all the bits are not set, then I have to traverse the adjacent nodes. Now I traverse the adjacent node, I calculate the bit mask after we visit that adjacent node. So this bit mask takes the account of the visited neighbor, and I prepare the tuple for the visited neighbor. How? This is the neighbor itself, this is the new bit mask for that neighbor, and this is the cost. Okay, so this is not mask, this is cost. So the cost increments by 1, and after that I have to check if I haven't explored that path or not, because if I already have explored that path, which is represented in this bit mask, where we end that path at this node, then we don't have to push this pair, we don't have to push this node. Otherwise we push it into the set and we push it into the queue. So whenever we arrive at the node where we have all the bits set, we return the cost right from here. So this is just a multi-source BFS. Well, if we never arrive at a node, that means there is no path which is all the nodes of the graph, then by default we return -1 from this function. Fine, so this is how it's working. I hope you got where we are going. Let's see the implementation. Okay, so this is the solution class. Let's create the tuple. Let's create the structure for the tuple. So here we have our structure. In the structure we have three things. We have node, we have a mask, and we have the cost. Then let's create the function. Let's call it. Okay, so this is the shortest path length function which takes in the graph. Let's calculate the size of the graph. So this will give me the number of nodes that we have in the graph. Now let's create a queue of the type tuple, which will be used to store the tuples. Let's call it queue, and we push the tuples for each node. So we start from node 0 to node number n minus 1, and for each node I will have a tuple. So struct tuple, let's call it head, and in this head we'll have three things: the node, the mask corresponding to that node, and the cost, which is 1, or let's say 0. Let's push 0. Now we push this tuple into the queue. We also have to keep track of a set of pair which will store the node along with its bit mask, so that we are sure that we do not revisit a path again. So let's call it st. So we also store the pair for this st. So we store the node and its mask, which is this. Fine. And we push this head into the queue. So this head is pushed into the queue, and we push it for all the nodes. Now let's start our BFS. Till the queue is not empty, we run the. So let's extract three things here. The first, let's extract the top node from the queue, or the front node from the queue, and okay, and I pop this node from the queue and check if the mask for this node, that is mask, if this mask corresponds to all the nodes visited. So if it is the case, then it would be equal to 2 raised to the power n minus 1. So in this fashion, if this is the case, then I will return the cost right from here. So what is the cost? Tup dot cost. If it is not the case, then I will have to traverse the child nodes or the neighbor nodes. So I traverse the child nodes, and here I have to check, and let's calculate the mask for, let's calculate the bit mask for the new path. So I'm adding this child here. So I will calculate the bit mask like this. So the initial bit mask till this node is tup dot mask, and I have to OR it with 1 raised to the power child. So this will give me, so this will set the corresponding position for this child to 1, and hence adding this child into the path. Now here I have to check if this new path which I have calculated, if the set contains this path or not. So if the set contains this pair, which is unique for each node, if this contains this pair, then that means, okay, if this is not, so if this is not there, then that means I will push it, I will insert this into the set. So child bit mask pair is inserted, and add this new node into the queue. So queue dot push, add this new node which contains this node number child, the new bit mask, and the new cost, that would be tup dot cost plus 1. Fine. So in this fashion the BFS algorithm is executed, and if I never encounter this condition, then by default at the end I will have to return -1. That means I do not have any valid path where I visit all the nodes. Fine. So that's all. That's the implementation in C++. Let's see the implementation in other languages. So that's all for this video. If you like the video, then hit the like button and make sure to subscribe to my YouTube channel and for more such videos on algorithms and data structures. So I hope to see you in my next video.